Welcome back. I got a special treat for you guys. I don't know if you've ever seen one of these things before, but this is how we used to communicate back in the day, before we had smartphones. So this is called a telephone, and all it does is let you talk to other people. That's it. It doesn't have text. It doesn't have YouTube or anything like that. It's I don't know if you've ever seen one, but it's amazing if you look at the history of phones. I mean, originally there was just two wires, right? And those wires were physically connected. So you picked it up and you talked to the operator, who was just listening all the time. And then they started adding more and more automation to this thing. So originally all it was sending is voice signals. And then they wanted to send more and more information. They wanted to get it to ring the bell, right? That came later. And so they added a signal to do that. And then they added these pulses that you could dial. There used to be a dial on these things, and you would turn the dial and it would go tick, 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 tick. And there was a machine that would count those ticks and get a number out of that. So then eventually what they ended up with was a system where you could do these tones, right? And here, I'll turn this on and see if you can hear that. I don't know if that's turning it up, but there's two tones. Like when I push this button here, when I push the 3, there's two tones. So there's a set of frequencies. There's 3 frequencies along the columns, and that's called the high band. And then there's 4 frequencies on this way, so that's called the low band. So there's a frequency, and they're all below 941 hertz. Like this one's 941 and this one's 6 something. Okay, then there's there's actually 4 high band frequencies, one of which is on here. There's 4. So this column has a 1209 hertz and 1336 hertz and 1497 hertz. So they're sending 2 frequencies, and then you want to capture just those frequencies. And because the frequencies below that are used for other things, like to ring the bell and stuff. And then the higher frequencies, I'm not sure, but those might be used for certain things. I know that DSL, which is a way to send broadband, well, kind of broadband-ish, over phone lines, those use even higher frequencies. So you want to filter that out. And I don't want to wander too much, but the reason broadband's not available in a lot of areas is because it's impossible to send these higher frequencies over the longer distance lines. There's some limit on some miles, and it has to do with the impedance of the lines. Anyway, I'm wandering a little bit, but it all has to do with filtering and stuff. Okay, so the problem we want to solve, and I wrote it out because it's kind of long, is we want to design a bandpass filter that'll send just the tones that come out of these things. So there's 4 tones this way and 4 tones that way. We want to isolate just the high band tones, which are, let's see, this column is 1209, this column's 1336, 1477, and then there's another column not used for buttons, supposedly at 1633 hertz. And then there's 4 frequencies on the rows, and the highest column has 941 hertz. So our problem is we just want to filter out the high frequency band just to let that go through so that we can analyze that further. So we want to send just one of these 4 high band frequencies through, okay, and filter out everything else. And then we, as a measure of how well this high band pass filter is working, we want to analyze the attenuation of the highest low band. So the low bands are on the rows, and the highest low band is 941. Okay, so once again, we have 4 columns, only 3 of which are on the phone. They each have a frequency. That's these 4 frequencies. We want those to pass through, and then we want to filter out the low band frequencies here. And we're going to use 941, which is the highest low band frequency, as a test of how well our attenuator is working. So we're trying to do. So let's say this another way, because just understanding the problem is kind of hard. So there's 941 hertz there's 1209 hertz, there's 1336 hertz, there's 1477 hertz, and 1633 hertz. These are the high bands. These are the 4 high band frequencies that we want to pass. And then there's a low band. There's a low band of which we're only looking at the 941. We're going to need this in radians per second, so let's go ahead and put that on this table right now. If you do the 2 pi thing, you end up with 5912 radians per second, 7596. Let me draw some separators here, and then 8394, and then 9280, and then 10260. Okay, so these are the 4 high band frequencies that we want to pass, and then this is the highest low band frequency that we want to filter out. So we want to let the columns pass and the frequencies on the rows to be filtered. So another way to look at this is what they're saying is we want to make a bandpass filter. Okay, so it has an attenuation given by the magnitude of h at j omega. It looks like this. It has this shape. It's kind of steep, and then it gets a little more gentle, and then it goes like that. And it will attenuate somewhere between 0 and 1. The signals coming in will come out somewhere between 0 and 1, stronger or as strong as they used to be. Did I read this already? Design a series RLC bandpass filter for isolating the high frequency tones from a dual tone multi-frequency telephone. One of these. The L and C values, we want to find the L and C values that place the cutoff freaks at the edges of the high band freak. This is the high band. So there's a 1 over root 2, which is 0.707. There's 2 freaks that define the band. This is omega C1, which is 1209, or let's use the 7596. This is omega cutoff 2, which is 10260. That's what this is saying here. The cutoff freaks at the edges of the high band freak. The edges of the high band freak, these 2 cutoffs. So this whole high band between this band of frequencies, this range of frequencies, lowest to the highest, 7596 to 10260. These will make it through the filter because they will be attenuated no more than 0.707, which is considered the, acceptable. That we say that these signals get through because they're attenuated no more than 707, and we say anything below that, any frequency down in here will be cut off, and anything up in here will be cut off. Okay, then there's omega sub 0, the center frequency, which we're gonna, whatever that is. Yeah, and then so these 4 frequencies here, this defines the pass band and the low cutoff and the high cutoff. Okay, then there's another set of frequencies, the highest of which is this 941. We want that to be cut off, and as a test of how well it's working, where will it be? Like, it's going to be 5912. Where is that? Like, what's the attenuation value on that? And then these other 2, like in these middle 2, where are they? Like, there's going to be a freak in here. Where's that? And then there's going to be another one up in here. These 2 freaks, they're going to be on these two, this line and this line. And what are their attenuation values? I'll tell you right now, they're going to be the same, which is interesting. That's why these two middle values were selected, because they have the same attenuation. Now that may have something to do with the circuit that detects these frequencies. I don't know the details on that. There could be some mathematical reason, or it could be an accident. Who knows? Anyway, that's the problem. We're going to make a series RLC bandpass filter for isolating the high frequency tones, these 4 tones, from a phone. And we want to find the L and C values that will give us this pass band with these two cutoffs. So any frequency in this 4 frequency range will be attenuated no more than 1 over root 2. And then what is that attenuation? We would expect this one and this one, the cutoff frequencies, to be exactly 0.707, because that's the problem description. Part A is saying that. But these two middle frequencies here in the high band, they should be attenuated less, because they're in between these two cutoffs. And then part C is asking, what about this lower frequency, this highest low band frequency? Where will it be on here? How much will it be attenuated? That's what they're asking for. All right, that's 10 minutes to explain what the problem is even asking. The circuit that we're going to get is going to look something like this, because they're asking for a series. They're asking for a series RLC. That's this guy. And there's some input voltage. And then we're measuring this. We're listening to this thing here. And certain freaks are going to get through on this V0 a little better than other freaks. And and this R is 600 ohms. That has to be given. So they give you that. We just need to find the S and the C and the the C and the L value. Okay, that's the problem. So part A, we just have to play with our math equations that were given. Different equations, just sort of like pick ones, sort of knowns to unknowns, basically. Like, for example, we could calculate beta because we're given the two cutoff frequencies. And the bandwidth is this thing right here. Between the two cutoff frequencies is beta. So we can find that right now. That's knowns to unknowns. We're given these two knowns, C2 and or the omega C2 and omega C1, the two cutoff frequencies, so we can calculate the bandwidth, right? So let's do that. So it's 10 to 60 radians per second, this high freak minus this lower freak. Okay, these are the high and low frequencies on the high band. And you end up with 2664 radians per second, which we're going to need that. And then, so we used this thing. And then we could use this L is R by beta. That's one of our formulas. That's the definition of bandwidth for the series. Okay, we have this formula. So it's 600 over 2664. It's 0.225 henries so far. Pretty easy. Then we can use this thing, this 1 over LC is root the product of the two cutoff frequencies. Okay, this was in the recipe book of formulas that were given. So we can solve for C is the only unknown in here after we've gotten this far. So C is just 1 over L omega C1, omega C2, solving this thing here for the capacitance. So it's 1 over 225 henries. 7596 is the low cutoff freak, and 10260 is the high cutoff freak. You end up with 57 nanofarad. That's the L and the C values. That's part A. Okay, that was pretty easy. Then the attenuation freaks. So these sort of come out together. B and C is the attenuation freaks for each of these high band freaks, and then that's another test. What is the attenuation freak of the low band? What is the attenuation of the low band freak? So, so B and C is asking for the attenuation of these different freaks. So from the graph and the problem description, in part A, you're asked for L and C values that place the cutoff freaks at the edges of the high band freak. So they're giving you these two cutoff freaks. And the definition of a cutoff freak is the freak at which the attenuation is 0.707. So the answer, you have two answers already. So for 1209 hertz and 1633 hertz, these two, the two cutoff freaks, the attenuation is 1 over root 2, because that's by definition. So you could write that out in different ways. So the way the book writes it out is the magnitude of the voltage at 1209 hertz is equal to the magnitude of the voltage at 1633 hertz. And that's going to be 0.707 of the peak. That's just I don't know. It'd be fine if you just said 0.707, but this is, we're trying to say that the peak voltages of these two freaks, if the signal coming in has these two freaks, it will be attenuated by 0.707. A little bit verbose way to say it, but anyway. So that's the two cutoff freaks. It's really by definition that those are 0.707. All right, now we need to solve for the attenuation at these two middle freaks and at this this one low frequency. So to do that, we need to do a little bit of cranking, some math. So we're going to use the transfer function, which for a bandpass filter is given by beta s squared plus beta s plus omega 0 squared. Beta is the band width, omega 0 is the center frequency, right? There's the center frequency, omega 0, and beta is the bandwidth. And we're going to solve this we're going to use 3 times to solve for these two middle freaks and then this freak. So it's worth it to do some pre-cooking here. So omega 0 we can solve for now. So this is going to be 1 over root. We've got this formula, which was this here. We just didn't use that part, but now we need this part. So omega 0 is a square root of 1 over LC. So 57 times 10 to the minus 9th, 57 nanofarad, and the capacitance is, that was the capacitance. And then the inductance is 225 henries. Root of all that junk, you're going to end up with 8830 radians per second. That's this thing here. You could write it in here if you want. 8830. So we can plug this value into omega 0 in the transfer function, and we know beta as well. So we can cook this a little bit better, and then we can plug in j omega for s. So if you do that, so you plug in some stuff, what you're going to get is h of j omega is j beta omega, or beta j omega if you prefer, over j omega squared s squared. Beta s is beta j omega, and omega 0 squared is omega 0 squared. And then this guy here, the j becomes a -1 when you square it. So you get j beta omega, and the middle term is beta j omega, and then this term plus omega 0 squared. And this guy becomes a minus omega squared. So omega 0 is a constant and omega is a variable. And then plugging in these numbers, so we know beta and we know omega 0, those are constants. We'll get a function of a variable omega. So this will be 2664j omega over, just plugging in beta, and that, okay, plugging in beta, and you get 2664j omega, and then omega 0 squared is 8830 squared minus omega squared. So lastly, h at j omega is 2664j omega over 2664j omega plus 77.9 times 10 to the 6 is 8830 squared minus omega squared. So this is h of j omega, just a function of omega. Okay? Now we can solve this. We can use this to solve for the attenuation, which is the absolute value of this guy. We can solve it 3 times for these two middle frequencies and then this low pass, this low band frequency. Okay, so we've got this hj omega. It's a function of omega, and we're going to solve, let's call this Bob. So we're going to solve Bob at various frequencies. So we need to solve it at, one of them was 1336 hertz. All right, so h of j, and 1336 hertz was 8394 radians per second. So it's going to be 2664j 8394 j omega over 2664j 8394 plus 77 times 10 to the 6 minus 8394 squared, which is j 22.4 times 10 to the 6 is the numerator. These two numbers, you get j, same thing, j 22.4 times 10 to the 6 plus 77 times 10 to the 6 minus 70.5 times 10 to the 6. These 10 to the 6's go away, and you end up with j 22.4 over J to 2.4 plus 6.5. It's two complex numbers, so you put those into your calculator and you get another complex number, 0.922 plus 0.267J. And if you put that in polar form, you get 0.948 with an angle of 16.18. This is the attenuation of this middle frequency. Okay, do that 3 more times. So at 1497 hertz, the equivalent angular frequency is 9280 radians per second. Plug in all that stuff, so you get 2664J. Plug all that stuff into Bob. 9280, and then denominator 2664J 9280, same thing, plus 77 times 10 to the 6 minus 9280 quantity squared, or squared, which is J 24.7 times 10 to the 6 over J 24.7 times 10 to the 6 plus 77 times 10 to the 6 minus 9280 squared is 86 times 10 to the 6. Once again, the 10 to the 6's cancel. You end up with J 24.7 over J 24.7 minus 9. Divide those in these two complex numbers in your calculator, and you get 0.88 minus 0.32J, complex number in rectangular format. Convert this rectangular format complex number to a polar format complex number, and you get 0.948 with an angle of minus 20 degrees. And this is the attenuation. So these are the same attenuation value. It's not a coincidence. Right, and if you solve this one more time at 941 hertz, you're going to get H at J 940 5912 radians per second. And you go through this whole thing, and you're going to get 0.344 with an angle of 69.8 degrees, and this is the attenuation. So what that means, the two cutoff frequencies have an attenuation of 0.707. That's by definition. The two middle frequencies in that band have the same attenuation. That's how these two frequencies were chosen, is because they wanted them to have the same attenuation for some other reason. They don't, which you could look up, historical. Sometimes the reasons are partly historical, sometimes they're partly by design. And then the filter is trying to filter out this guy, and you can see by the attenuation that it's much, much lower. If we stick these on the plot, these two middle band guys, they're 948, so that's these two these two frequencies in the middle. Well, not the middle, but inside the band here, inside the cutoffs, they get through with a pretty good strength, 95% strength. The cutoffs get through with a 70% strength. But this low frequency here, this 5912, it's attenuated down to 34%. Not going to do it. Was going to call 911 right there, but it's a joke. Okay. That's it.